We'll now do an example of geometric Brownian motion where we can see the relationship of the various formulas that we looked at earlier. So let's imagine we have a price of x at time 0, which is initially 100. And then we'll use a geometric model, geometric Brownian motion, where dx will be 10% of x dt. And then we'll have a 20% of x dz. So intuitively, if this were a stock price model, we're basically modeling a stock whose initial value is 100 and has an expected annual return of 10% and a variability, a standard deviation of that return of 20%. And this is using the continuous model of returns. So first of all, we have an expression for what is the differential of the log of x, the natural log of x. And that's where we pick up the adjustment to alpha. The log of x, if x is geometric Brownian motion, log x is arithmetic Brownian motion. And what we get is an expression 0.1 minus a half times the 0.2 squared dt. And then we have the same 0.2 dz. So we have an adjustment to the alpha minus a half sigma squared. We have the same sigma, but of course we do not have an x. This is arithmetic Brownian motion, all numerical coefficients. And we end up here with 0.08 dt plus 0.2 dz. So this is saying that if x as a stock price has a continuous return which on average is 10% with a 20% standard deviation, then in fact the log of x will have a mean drift of 8%, and again it'll have a 20% absolute standard deviation. So we can now say that if this is the formula for the differential, we can write down the formula for the log of x of t. And the reason is arithmetic Brownian motion adds up. This is saying that the differential of these logs is our normal random variables. This is saying that each one of these differentials is a normal distribution with a mean of 0.08 dt and a variance of 0.2 dt, 0.2 squared, I should say, dt. So to go from the differential of the log to the log at a future point in time, I need to add up a bunch of differentials. Well, that's easy because each differential is normal, and if I add up normals, I get a normal. And consequently, this log can be expressed as 0.08 times t plus 0.2 z of t. And this is saying that the log of x at time t is normally distributed with a mean of 0.08 t and a variance of 0.2 squared times t. Because remember, z of t has a variance of t. From that, we can use the formula. We can just do an exponentiation, and this says that x of t can also be expressed as 100 and I'm sorry, I have a mistake here. I would have to have in here a log of x of 0. That keeps falling out of my equations, I'm sorry. But if I add up my dx's, I have to start from some place. And so the log of x of t will start off with the log of x of 0, and then all of my increments will get me to the final answer. And so in this normal distribution, I also must add the natural log of x of 0. So from that, I can now exponentiate that formula, and I get x of t is equal to x of 0, which is the 100, times e to a normal variable. And that normal variable has exactly the mean we started with, 0.08 t 0.2 squared t. And finally, I can say, okay, now I have a model for what x looks like at time t. What's the expected value of this? And that comes from the moment generating formula. And the expected value of this is 100 e to the 0.1 t. In other words, even though the average return is 8% per year, when I look at the expected value of x of t, it reflects a return of 10% per year. So it's the difference between the expected value of x and the expected return. And what we can see is that this is the return for the expected value of x, is 10%. That's a way of saying it. The expected return is 8%, that's what this says, and what this says is that the return you get for the expected stock price is 10%. Hopefully that clarifies these various formulas. Okay, we're now going to be moving to the next module.